Let's begin as we always do with store buffering. So here we have a little schedule for 2 different cores, and we're going to assume that the instructions happen in the order they're given. So over here on core 1, we have 2 instructions. We take the value 1 and we store it at the location pointed to by foo. Following that, we take whatever the contents are of location bar and we move it into the register or the processor variable called RAX. So the address pointed to by foo, we put a 1 at that location. The register RAX, we store the contents of bar in that register. Over here on core 2, we take a 1 and we store it in the location bar. We take the contents of location foo and we store that in the register RBX. Simple stuff. And there are many different ways we can play these events out. Even though we know they're going to happen in this order and they're going to happen in this order, there's many different ways that it can happen. In fact, there are 6. We can do everything for core 1 followed by everything for core 2. That's the first schedule. We can do everything for core 2 followed by everything for core 1. That's the second schedule. And we could do the operations for 1 in here. So core 2 does its first instruction, then everything on core 1 happens, and then core 2 does its, and so on and so on and so on. Now, I realize these things can happen simultaneously, right? Happen at the same time. But what we're looking at is the effect. And since these are affecting the contents of memory, it makes sense to think about which one gets done first. And so this schedule sort of does, these schedules sort of do make sense. Okay, core 1 and core 2 are running simultaneously, but now they're having to do something with some memory, and that requires that you interact with the cache, and that can at least in some sense serialize some of the instructions that are happening. But there's only 2, 3, 4, 5, 6 possibilities, and if we look at those, you'll see here we move some 1s to foo and bar, and then we get foo. We move some 1s to foo and bar, and then we get bar. Move some 1s to foo and bar, and then we get both bar and foo. Same thing here, same thing here, same thing here. It's clear that we're going to end up with a 1 in RAX or RBX, no matter how these things end up executing. No matter how they happen, we're going to end up with a 1 in either foo or bar, just because, right? So in every execution order, at least one of those reads gets a 1. Suppose we start with a 0 in both locations. So here we go. Let's pick a particular schedule and look at it. Here we put 1 in foo. The processor gets scheduled to write a 1 to the location foo. Then we are going to read the contents of bar and put it in RAX. Let's say the processor reads the value 0 into RAX. Okay. Now we do this, put a 1 in bar. The processor is scheduled to write a 1 to the location bar, and then we take whatever's in foo and put it in RBX. But wait, we scheduled this right up here, but it may not have happened yet. So because the write to foo has not yet happened, it's pending on another core, the read from foo gets 0. In fact, thanks to store buffering, we can end up reading 0 in both cases, which, if you look back here, that was not possible if these schedules happened as we saw, but it is possible because of internal store buffering in the processor, which means that even though we explicitly told the machine what to do, once again it didn't do it. And of course, there's a paper about this rogue in-flight data load, and there's lots of mischief you can get into by exploiting this, and you can read all about it. And of course, there's a way to prevent this, and the way to prevent it is to protect critical code with a memory fence, and that's the mfence instruction. It may not be put in explicitly, automatically by the compiler. You may have to take action to put it in yourself to ensure that certain things happen correctly. This homework that's coming up due on the 13th. The homework is to revisit your previous threat model and reapply the stride approach and indicate any new threats you found. So you should be turning that in. Hopefully that went well and you learned some new stuff. So instead of the usual class, what we're going to do today is maybe a little bit different. We're going to take a look at an actual system. We're going to sort of dive into the architecture for it. I think of this as a kind of almost pathologically secure system, and you can see some of the thought that went into creating it. So this is a project called the Black Box, and the purpose of it is to have a secure by design architecture for data sharing and analytics, and not just any data sharing and analytics, but specific data sharing and analytics. The design focus for the whole system was to minimize the attack surface. Reduce the attack surface until it's just tiny. And the only failure mode we permit for this system is data destruction, right? The data is the thing you want to protect. So if someone begins to break through, you destroy the data. And we want to build all of this using standard protocols and off-the-shelf stuff because we don't want to have to invent a whole lot of new things to make this work. So the idea here is protecting the data by design. We use a combination of physical and network and other design issues and severe restrictions on installed software to minimize the attack surface. Even better, we don't let anyone have read or write access to all of the data except for internal data access and analysis code that's been explicitly vetted. So the system administrators in the building can't get access to this system. The people who wrote the system and are maintaining it can't get access to it when it's running and there's data present. And there's no communication with the outside world except for data exchange with previously determined clients. And finally, there is no persistent storage of any sensitive data. Now, why are we doing all this? Well, this is all done to support a process called the routine interstate duplicate review. So people who are living with HIV or AIDS can be put on a regimen of drugs. If that happens, then their viral load will decrease to the point where they can't transmit the virus anymore. If we get enough of a percentage of people with the disease below that threshold, the disease stops spreading and can be reduced. And that's what we want. We want to reduce the incidence of AIDS in the general population. The way to do that is to get people who have AIDS on the successful drug regimen. It improves their health and it improves public health. One of the problems is keeping track of who's on it and who's not, and then making sure people who are not on it are made aware of services and support that can help them. To do that, we need to be sure that everyone is being properly addressed. And it turns out people are messy. They do things like move around. Someone who lives in, let's say, Northern Virginia might work in DC, and they might, because it's convenient, actually see a doctor in Maryland. And in that situation, it's very difficult to say who's sort of responsible for the public health aspects associated with that person. Right? So Virginia may not even know that person has HIV/AIDS. Maryland might know it, but that person doesn't live there. And DC is probably aware of it, or may not be aware of any of this at all. So how do we address this? Well, it turns out that the solution is to have every state call every other state and go over their list with them to be sure that we figure out who owns which person and where they are and who should be supporting that person's health. That's a complicated process. There are more than 50 public health jurisdictions in the U.S. I forget how many there are. I think it's something like in the 80s. And so they have to call each other. They have this N-by-N problem because people move and they change their name and they go places that maybe are outside of their state, and it can become complicated. So Georgetown University developed a matching algorithm. If you give us all of the data for all of the states, we will do this N-by-N match in a very efficient way. And we can use things like the Soundex algorithm. So if you have a Smith, S-M-I-T-H, and you have a Smith, S-M-Y-T-H, you can match them. And we can actually define levels of matching and perform the match and then notify everybody of the results. The problem is, if you put all of this information together in one place with names and addresses and other personal identifiable and public health information, you run the risk of somebody getting all of that, and that's not good. So we need to protect this very, very, very carefully. So Georgetown, like I said, developed the match. They'd already done a match with a specialized environment, and they wanted a much more secure environment to do it. And so that led to the Black Box Project. And so here are the requirements more specifically. No sensitive data is persistently stored or ever written to non-volatile storage. In fact, let's just not have hard drives in the computers. Okay? While they're running, everything can just be in RAM. And that means you need a lot of RAM. It turns out putting a terabyte of RAM in a computer is expensive, but doable. Data destruction is the desirable failure mode. So if anything goes wrong, one of the things we can do is kill power to the machine. Because since the machine has no persistent storage and everything's in DRAM, if we kill power, we introduce error into the DRAM and the data is effectively corrupted. No single party owns all the keys used. That's cryptographic keys for communication. And one set of private keys is volatile and not human accessible. So when the system is running, the system can generate a key, store it internally in DRAM, and then when power is lost, that key is lost. Data will be doubly encrypted in transit and encrypted at rest. So if you remember last time we talked about data in transit and data at rest, when data is sitting in the memory drive of the machine, it's encrypted. When it's in transit to public health institutions, it does so over a doubly encrypted channel. Endpoints for all the transfers are well known and defined in advance. We can do that because we know Maryland's public health, their office has this IP address, and that's the only IP address we'll accept from them. California has this. Houston, which has its own, has this, etc. And finally, the hardware should be inaccessible while sensitive data is stored. And we'll see how we achieve that. So here's the basic infrastructure for it. This was built at Oak Ridge National Laboratory. And here you see some of the states that participated in the early round. They talk to us over the internet. That's where all the good stuff is. And come here to an external IP for Oak Ridge National Laboratory. The data then travels through the Oak Ridge network to something called the Knowledge Discovery. I forget what the I stands for, but Knowledge Discovery. And that's a specialized environment that has its own security, has its own firewall, its own data controls. Once you're inside there, we get to the actual cabinet that holds our stuff. And you see there's only SSH, SFTP connections that are permitted here. And you're inside the cabinet. There's a power interlock. We'll come back to that in a few moments. But there are three main computers in here: an external, a compute, and a management node. And you see the network interfaces are well defined. right? So there's a specific network interface card. There's an actual port on this machine that is plugged in to go out. There's one that is specifically hardwired to connect to compute, one that is hardwired to connect to management, and compute has one that connects to external, one that connects to management, and then management has specific ports that connect to compute and external. What's this power interlock? Well, the idea is if the cabinet is open, power's killed. It interrupts power. The cabinet has to be closed for power to flow. So the way that you power the system off is you open the cabinet. The way you power it on is you close the cabinet and everything powers on. That means if you want to get to these, to plug something in, you have to open the cabinet, which interrupts power, which kills all of these. Since everything is in DRAM, you lose all that information. There is a drive here on management that is used to boot the system and for nothing else. We'll talk about that in a bit. But this is the basic architecture, and you'll see there's physical parts to it, and there's logical parts and network parts to it to make it work. Communication is similarly pathological. One of the things about the external node, which is the only one that has a connection to the outside world, is that all of its ports are set to be closed. It has no external open ports, which means that if you try to scan for it, it's like there's no machine there. No ports will issue a response. So how do we talk to it if all of its ports are closed? Right? I mean, that's good. That minimizes the attack surface. But really, how do you talk to the machine? And the answer is you use port knocking. So we'll come back to that in a moment because I need to explain to you a little bit about how ports work on a computer to make that make sense. But first, the client will generate some keys or it will select some data. So it either wants to exchange new public keys with us or it wants to exchange some data with us for matching. It issues a port knock, which basically is a way to tell the external computer that it wants to talk. If the external node recognizes the knock, it will then either generate and position a new set of volatile keys, or it will position data for exchange. And then over here on the client, we start up an SSH server. The SSH server starts on the client on the remote machine over, let's say, in Virginia's public health department. And then the external node reaches out and connects via SSH to the client, to, let's say, Virginia. So the client didn't connect to the external node connected to the client, and it did that because of this port knock. So let's stop for a minute and really quickly think about what that means. A port is nothing more than just a number. A packet arrives at the computer and it specifies a certain port on the machine. The kernel gets the packet regardless of what's going on, and it looks to see what port is this going to. And it can check its tables, which say that all ports are closed, and so then it discards that packet. But before that packet is discarded, you could, for example, take a look and see what port it went to and got rejected. And you can keep track of the packets that come in from a particular machine, and if they match a certain pattern, we call that a port knock, and you can then trigger a set of actions, and that's in fact what happens. So a series of packets come in, and they match the action for, let's say, Virginia's public health department, and that tells us to get things ready to talk to Virginia and then connect to Virginia's known IP address. Not necessarily the IP address that sent the knock, but the one where we know Virginia is and should be waiting. So if somebody who's not Virginia sends this knock, too bad, we try to connect to Virginia's IP address instead. So the SSH tunnel is opened. There is an authentication phase where the two machines authenticate each other and where the external node authenticates itself to the client. Lots of keys are involved in this, more than just one pair. because we also do host authentication, and we have to have host keys. Once that's authentication, let's say it passes, the client now starts an SFTP connection back to external. The external node only accepts SFTP. It does not accept SSH with shell connections. It only accepts SFTP connections. So that comes back, and you may wonder, how can that happen given that all the ports are closed? Well, this goes back over the initial SSH tunnel. So port 22 outbound is open for this, and this comes back over whatever that connection is. So this tunnel happens, that's the outer tunnel, and then this comes back over the inner tunnel. So now we're trying to do a new connection, so the SSH authentication methods happen again, but in the other direction. And so there's more keys involved to make that happen. If that succeeds, now we have a fully open, doubly encrypted connection, and we can exchange our keys or we can exchange data. So remember, if they say they want to do a key exchange, we generate new keys stored on the external node, a private key which is stored here which no one can get to, and we exchange the public key with them. And then subsequently, when they want to talk, we would use that key. Connection gets terminated, we store the data or the keys, and that's it. And so this is how you allow communication with a node when you don't have any ports open and you want to be sure that it's very, very difficult to connect. There's lots of protections in this. I would love to go through the threat model for this and the attack model and all the other models we did for it, but for lots of reasons I can't, right? They expose information about the environment that we don't necessarily want to make public. So I'll just hit some of the highlights. And there are physical protections, network protections, internal protections, there's data protection, and even protections for the client in this. The physical protections, some of them we've talked about, but the system is located in a secure environment. It's in a locked cage with a few other different projects. In a secure environment, inside a secure computing center, inside a secure building, inside the Oak Ridge National Laboratory. And so it's secured in an environment with full-time camera monitoring with people who actually do watch it, and so it's physically protected. The physical system is located in a cabinet that includes a power interlock, so that if you lose power, all the data is lost. So if you open the cabinet, you lose the data. Sensitive data is exclusively stored in encrypted volatile memory. And since the keys themselves are also stored in the running memory, if anything gets corrupted, you've probably lost the keys and therefore you've lost the data. So even if you could run in there, spray the thing with Freon, pull the memory out, and then paw through it, you'd have to find the keys in the encrypted file system, and it would be very, 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 very challenging. Network interfaces are restricted to specific dedicated connections. We don't accept connections from anywhere. All modifications to software and hardware are subject to a two-person rule, meaning that the two people who are in charge of the project have to observe the changes and agree. And all support and analysis software is reviewed and approved by at least 3 people prior to installation. So there's a lot that goes on to protect this. In fact, the machine that's used to produce the images that boot it is a machine that's off the network and stored away. Network protections: no incoming ports are open. Outgoing connections are only permitted to known and defined endpoints, and we can actually enforce that through the switch that connects the machine to the rest of the network. Data transfers are doubly encrypted, 2 SSH channels. Authentication is done by 4096-bit per client keys with 1 key purely volatile. It's stored only in the volatile memory inside the system that you can't get to. Internal protections: The external node of the black box does not permit a user to run an interactive shell. Any user. In fact, we set the shell for root to be dev null. So no one can run an interactive shell. Turns out you can do that. You say no one's allowed to run a shell. So even if you could get in there, you can't run any of the shells. The SFTP connections are restricted to what's known as a root jail. If you don't know what that is, the idea is we change the root directory. So the root directory for you is the directory of your particular home area, and that's it. So you can't CD up because there is no up. You are locked into your little home area. So even when they connect by SFTP, they're dumped into this jail, and they can't get access to anything except their little area of the network. So Virginia can see its area, Maryland can see its area, but they can't see anything else. It's like other parts of the file system don't exist. External and compute nodes have no persistent storage. Again, no spinning drives. It's all DRAM. The external node of the black box is itself treated as untrusted by the compute node. Okay? The compute node will not accept connections from the external node. How does data get there? Well, the compute node has to explicitly connect to the external node and then copy data over. And we'll see some of what happens when that happens. Input data does not remain on the external node. It's periodically moved to the compute node. So even if someone somehow got into the external node, the data is probably not there anymore. And software running on the black box is whitelisted, and the self-check is done at boot to be sure that nothing else has been done and the image hasn't been tampered with. So, how about data protection? All the components treat the data as raw text, and we are careful to do that. We don't use languages that might allow you to interpolate into the strings. We are very careful of saying this is raw data that's supposed to have a structure to it. Prior to transfer to the black box, the data is validated. So data on the client validates the structure of the data. It has to be in this specific format. If it is, it's transmitted to the external node. The external node checks it again. If it doesn't match the format that's required, it discards it. The compute node checks it after a transfer. If it doesn't match the correct format, it discards it. When data is staged for retrieval, if it doesn't match the format, it's discarded. When it's sent back to the client, if it doesn't match the format, it's discarded. Everybody along the way is verifying that the data is properly structured and formatted. And the solution, if anything goes wrong, is to throw it away. Okay? So if fields aren't the right length, if they don't match the length that's defined in the file, if the information is not the kind of information that should be in there, gone. Client protection as well. We don't necessarily control where the client is, but we can control some information about it. The client is subject to the requirements of the jurisdiction where it's located, so they have a machine with whatever's required, antivirus, monitoring, who knows. The client has to have appropriate endpoint protection software. The client can be powered off when not used for a transfer, and in fact, what we recommend is the client software and the persistent keys be on a removable drive that can be locked away when not in use. So you want to do a data exchange, you go and get it out of the safe, you plug it into a computer, you start it up, you run it, you do the data exchange, you take it out, put it back in the safe, and lock it up. And so here's the black box system. And you see Jeff Nichols, one of the people who worked on the project, doing some work right here, helping us get it all configured and set up. Because it's dead inside here, you need another computer to do your work, and so we wheel one over and be able to do it. System is installed and configured. We've done successful tests, and in fact, since this picture was taken, we have shipped the whole thing back to Georgetown for long-term use. This was a major, difficult project to do, in that, as you can imagine, it's very hard to debug. You're on the phone with some external jurisdiction like Maryland, and you're like, okay, try this now, and they try to do the exchange, and maybe it happens, and maybe it doesn't. And how do you debug it? Well, it can be very, very challenging. So, okay, a very high-level threat model. The protections we saw earlier came from trying to mitigate threats we identified in the threat model. And the threat model for black box included nation-state actors, privileged insiders within IT, physical intruders into the building, and unwitting threat actors through social engineering. So we picked like the worst cases we could think of for this. And the threat model included the possibility of compromising remote clients. The idea being that it should be much easier to compromise, let's say, Maryland's public health infrastructure than it is to compromise the black box. So you might get Maryland's data, but you don't get everyone's data. Threat models are often privileged artifacts since they reveal information about the network, in this case about Oak Ridge's network and the KDI infrastructure and so on, and so we can't take a look at that. But we can take a look at some of the pieces that might go into that. So early on I told you to draw a picture and show the information flows, and your picture might look something like this, right? Jurisdictions, the internet, switches, the external node and compute node, and the management node, and so I can sort of lay out the pieces at a very high level like this. And that gives me the sort of the initial physical architecture. So then I can put information on here about what's traveling these links. Medical records in the eHARS format are traveling through an SSH tunnel over another SSH tunnel. Medical records in the eHARS format are traveling over this SSH tunnel. iPXE information is traveling over here. In fact, the management node, after these guys boot, it shuts down. So you close the cabinet, and then you watch for the light to go off on the management node to know that everything is successfully booted. So let's say a participating jurisdiction sends corrupted data, or it's compromised and it sends malware. How do we deal with that? We have to think about that. And that is part of this pathological, continually checking the data for proper structure and format. An intermediate actor intercepts traffic, that's a man in the middle, by some means. They do BGP poisoning or ARP poisoning or DNS poisoning maybe, so that they can pretend to be Virginia and get their data. Well, they have to have the keys that Virginia has, and in order to be able to establish that connection. And even if they can, and they're successful at all of that, they only, at most, get the results of the match for Virginia. Right? The data for Virginia owns that, sends it up to do the match. The result is just the result of the matching. And that's all they can get back, is information that says, this person in Maryland may be this person in Virginia, and that's it. Another project in the data center results in a network compromise. So that could be a possibility. So the network inside the data center gets compromised. Well, that's okay because everything on the network is doubly encrypted. The Oak Ridge physical network is compromised. That's more troubling, right? Someone fishes a cable out and splices into it. But again, everything, even the connections between the nodes inside the cabinet, is encrypted. What else might happen? Errors on the external node result in passing corrupted data to the compute node, so the compute node has to check the data. An error on the compute node might pass corrupted data back to the external node, so it has to check. The build computer might be compromised, so we store that away and we use the two-person rule to verify what's going into it. In fact, we use a version of Linux that's very stripped down, made for embedded computers, and we just have the minimum amount of software on it so we can actually look at what goes on it, walk through that file and verify that the correct stuff is checked. An insider installs a compromised image on the management node. How do you deal with that? Well, there is checking of the images on the management node thanks to the two-person rule and checking the hashes. Client generates weak cryptographic keys. Well, we actually specify how they're going to do it, and the client software does it for them. And our stuff will only accept certain strength of cryptographic key. The client's network gets compromised. Again, if that happens, maybe they can get the client's information, but they can't get other information. And And, we can't really control that. But we can control what information we pass back. An intruder attempts to fish out a network cable and splice it. Well, they're all encrypted. An incorrect algorithm on the compute node exposes information. That's on the compute node. So we have the compute node running. It computes something, and maybe it includes information for an individual who's not in the match, and somehow puts other information in there. It goes to external node and goes out. Well, again, the format of the data return needs to be such that that is very, very difficult. You can't just include arbitrary data in the data return. So all things we had to think about. New homework. I want you to go and read about Keras and get familiar with it. There's the link, and you can go ahead and use those to go in and experiment with it. It's a modeling tool, and you should try putting your system in it and seeing how it works. There's nothing to turn in for this. I just think you should get familiar with how one of these modeling tools works. And that's it.